Okay, here's an example problem of solving a system of differential equations with Laplace transforms. Now, this system is easy enough that we don't really have to rely upon that form we just arrived. When they're more complex than this and they have all the terms, that's useful. But in this case, we can just go ahead and brute force it, all right? I'm going to take the Laplace transform of the entire system, and this is what that's going to turn into. Our next line is going to read the Laplace transform of y1 prime is going to be s y1 plus y naught, and y naught is 1, so plus 1. And then that's just going to be the Laplace transform of y2, and that'll equal 0. So that's my equation 1. Oh, this is a minus. That's better. Okay, now let's do the same thing to the second equation. Second equation is just going to be y1 plus, again, the Laplace transform of y2 prime is going to be sy2 minus y2 naught, which is just 0. And then that will equal the Laplace transform of 2 cosine t, which is going to be 2s over s squared plus 1. Okay, so there's our system. This is what we need to solve. So let me rewrite it. What I recognize here is that it's almost an identity matrix. We're going to have S1, 1S as our coefficients times Y, and then that equals the answer matrix, which is going to be 1 over 2S over S squared plus 1. I mean, after all, these are already kind of in matrix notation, so we may as well use that to solve the system. That means the solution for y is going to be equal to the inverse of this guy divided by its determinant. So it'll be 1 over d times s1, 1s inverse. And then that will be times this matrix right here. And I can go ahead and do this inverse really easily. For a 2 by 2, it just means negating this diagonal and swapping this diagonal. So, and I can write in the determinant too. It's just going to be s squared minus 1. And then the answer matrix is what it's multiplied by. So it's 1 over 2s over s squared plus 1. Okay, so let's work out first what the product is of the inverse matrix times this, and then we'll divide it by s squared minus 1 at the end. So this is going to be first s times 1, that'll be the first term in the upper, and then minus 1 times this, so it's minus 2s over s squared plus 1. And that's the top term. The bottom term is going to be the bottom line times this, so it'll be negative 1, and then plus s times 2s, so 2s squared over s squared plus 1. And then once I work all this out, it'll still be times 1 over s squared minus 1. Okay, well, let's simplify these by putting them over a common denominator. So in this case, it's going to be s cubed plus s minus 2s, and that's all over s squared plus 1. And then the bottom term, this is going to be minus s squared minus 1 plus 2s squared, all divided by s squared plus 1. And keep in mind that once all this is simplified, it still has to be divided by 1 over s squared minus 1. Okay, the numerator of this one is s cubed minus s minus 2s, so that's x cubed minus s. So s cubed minus s, and that's over s squared plus 1. And then the bottom term is going to be negative s squared plus 2s squared, so that's s squared minus 1 over s squared plus 1. And then remember, this whole thing is still times 1 over s squared minus 1. And this is y equals. And we're just about there. When I multiply 1 over s squared minus 1 times this one, it just leaves an s in the numerator. So it'll be s over s squared plus 1. And for this one, it takes out the whole numerator. So it's 1 over s squared plus 1. And as you can see, these now are easily recognizable. This is y1, this is y2, and if I apply the inverse Laplace transforms to these produce a y set of answers that is equal to s over s squared plus 1 is cosine, and omega in this case is 1, so it's just cosine t, and 1 over s squared plus 1, that's sine. of t. So there's the solution to the system. y1 is cosine t, y2 is sine t, and because we were given initial conditions, there's no constants to add. That's the solution. Now, in this case, this was a system that's probably easier to approach by another method because it was a lot of work. But if these constant functions, if the non-homogeneous functions get more complex, then turning them into Laplace transforms is way easier than trying to model them with undetermined coefficients or variation of parameters. Okay, so your homework tonight is to solve a few more just like this.